I'm a PhD student at the University of Queensland, and today I will illustrate using the MSA transformer for phylogenetic tree reconstruction. We know a long-standing question in biology is to learn the evolutionary rules from the sequence data. And in the past half centuries, biologists rely on the multi-sequence alignment and build the never joining of the. Okay. So in the past half centuries, biologists rely on the multi-sequence alignment and built the never joining of the maximum lambda tree to infer the evolutionary rules from the sequence data. However, the big limitation of the previous method it assumed alignment size evolved independently and didn't consider the implicit effects. And this year, the Nobel Prize tells us the power of AI, and we want to use the power of AI to address this issue. So we consider the protein languages models. When training the models, we need to randomly mask 15% of the tokens, and then the model was asked to predict the masked token given the surrounding environment. In this way, we learn how to capture the interaction of the columns. So of particular interest, we'll consider the MSA transformer, which takes the multi-sequence alignment as input. And it consists of the 12 layers. Of each layer, it also has 12 row attention heads and column attention head. And the past research illustrates that the column attention head encode the phylogenetic relationship. Based on this, we want to further addressing the following questions. The first one is whether the model rely on the information available within the columns to capture the phylogeny. And the second is if we can use the MSA transformer to build the tree, whether the MSA transformer tree are comparable to the traditional phylogenetic trees. If we're addressing this issue, maybe we can further explore the usage of the MSA transformer. So from our experiment design, we first collect the original multi-sequence alignment from the PFAM database, and then we regenerate 3 extra multi-sequence alignment that preserve or break the conservation information within the multi-sequence alignment. And then for each multi-sequence alignment type, we extract the embeddings and the column attention heads layer by layer. We got the never joining and the maximum lambda tree. So, and then this is a comparison between the traditional method and our method. We used the workflow here to got so-called embedding tree and attention tree. Then we benchmark the similarity that we built from the MSA transformer and the classical phylogenetic approaches. The tree similarity was measured by both the Robinson score and the cluster information score. The high score means the high tree similarity. So this is our result. We use the attention tree and the embedding tree against the never joining tree. We find that both embedding tree and attention tree show some similarity to the traditional phylogenetic tree. However, the embedding tree have the higher tree similarity. The second finding is if we build the tree from the original multi-sequence alignment and using the shuffle columns multi-sequence alignment, it will always give us the comparable similarity to the traditional phylogenetic trees. So it further suggests the MSA transformer rely on the phylogeny within the columns to learn the phylogenetic relationship. If that's the case, we want to know how to use the embedding tree for the phylogenetic research. So we first used the embedding tree to solve the problems of the RDRP domain. It's a conserved domain across all the RNA virus has used to be for the phylogenetic inference. And then we find the high concordance between our ML tree and the embedding tree. Our embedding tree, the grouping of our embedding tree displays the distinct RNA virus groups, and then it's the same as the ML trees. So it demonstrates the robustness of using the embedding tree for phylogenetic research. And then we want to know if we can use the embedding tree to address more complicated evolutionary problems. So this time we consider the RDRP domain because the origin of this domain is unknown to the public. So, and the past research identify 8 conserved proteins and built 8 single protein ML trees. But these ML trees lack resolutions, and several families were were not monophyletic. So, but we also built the embedding trees. Our embedding tree do not support the previous conclusion that the conserved protein have the same evolutionary history, but it instead support they are evolved independently. So we want our method to further complement the previous phylogenetic reconstruction method and to explore the evolutionary history of the proteins. That's all. Thank you for listening.
Audience, we can have the questions. Okay, so we have one virtual question. So, is there any data loss while shuffling the columns? And can you explain? Can a loss function be applied to that?
We didn't train the model. This is a Z-short prediction. We're just using the pre-trained model and extract the embeddings and connotation heads.
Thank you. So can you